brief introduction to some of the basic object-oriented programming concepts in MATLAB in our previous lecture, let's take a look at some more advanced aspects. We're going to do that through an example. We're going to create a data structure that's widely used in computer science, but is not built into MATLAB directly. Why do we need yet another data structure? Well, MATLAB is built around matrices, and they're extremely useful, of course, but they do have a disadvantage in that their size is fixed. For example, when we create a new matrix, MATLAB finds a place in the memory where it'll fit and allocates space there. Of course, MATLAB allows us to increase the size of the matrix later on, which requires allocating new space for the additional elements. There's no way around that, but the nature of a matrix and its indexing requires that the entire matrix must fit into one contiguous set of memory cells. So it's very often necessary for MATLAB to allocate new space not just for the additional elements, but for new copies of all the existing elements in the matrix as well. It has to do that because there's usually not enough empty room next to the existing elements to accommodate the new ones. MATLAB accomplishes this expansion by stopping your program in the middle of a command, allocating the new space, copying all the existing values into it, and then continuing execution from where it left off. It does all this behind the scenes, so we don't have to think about it. But when we're dealing with large matrices and frequent size changes, it can slow our program way down. It's for this very reason that in our introductory course we recommended that you pre-allocate the full size of every matrix. That's always a good idea, of course, but sometimes it's just not possible to know in advance what that full size is going to be. And that brings us to the answer to why we need another data structure. We need it to provide an efficient means for adding and removing elements frequently. One such data structure is the linked list. A linked list consists of a set of individual elements linked into a chain. Each element, which in computer science terminology is sometimes called a node, stores some kind of data, and it also has a field, typically called next, that points to the next element in the list. In the example that we're looking at here, the data is just a letter, and we have only 3 elements in our list: A, C, and D. The next field of the last element of the list is set equal to 0 in most languages. In MATLAB, it's set equal to the empty array. The next field makes it easy to traverse a list. You start at the beginning of the list, which in computer science terminology is called the head of the list, and follow the next field to move from element to element until you encounter a next field that's equal to the empty array. When you get to the empty array, you know that you've reached the last element of the list, which in computer science terminology is called the tail of the list. A variant of the linked list is the doubly linked list, whose elements have an additional field, typically called previous or prev, that points to the previous element of the list. Using next and prev, we can freely traverse the list back and forth from head to tail and back to the head again. If we need to insert a new item into this list, then instead of creating a new structure and copying the existing data into it, as we would need to do with an array, with the linked list structure we need only change a couple of next and prev pointers to make that happen. Let's say that we want to insert a new node in this linked list between the first and the second nodes. Let's look at the steps we'd need to follow after we've created the new node that we want to insert. And let's say that the data in the new node that we've created is the letter B. First, we'll change B's prev and next pointers to point to A and C, respectively, as shown. Next, we change A's next pointer to point to node B. Finally, we change C's prev pointer to point to B, and that's it. To make the figure look better, we can rearrange it like this. Ooh, pretty. But that's just window dressing. It doesn't make any difference if our depiction looks like a bowl of spaghetti. It's just a representation. Once the next and prev pointers have been set correctly, the node is inserted, and our insertion is done and dusted. One leftover thing is this node variable pointing to B. We can leave it alone, or we can clear the variable from the workspace, depending on whether we need it later or not. It's irrelevant from the perspective of the linked list, so out it goes. Now, if we needed to insert a new node at the beginning or at the end of the list, the algorithm would be slightly different. We would need to change the head or the tail pointer. You can also imagine how to remove an element by updating the next pointer of the element before it and the prev pointer of the element after it. Well, we're about to implement a linked list in MATLAB using our newfound object-oriented program knowledge, so we'll have to take care of all these cases. But first, we've got a problem. You might have noticed it already. What kind of data type do head, tail, next, and prev have? In most programming languages, for example C++, they would be pointers. The value of a pointer is an address in the memory that specifies where the data object pointed to by it is located. The MATLAB concept closest to a pointer that we've used so far is a cell, as explained in our introductory course. While one might be tempted to try to implement a linked list with cells, any such attempt will be a dismal failure. The fundamental problem is that any implementation requires that two pointers point to the same node. For example, in our 4-element doubly linked list here, A's next pointer and C's prev pointers both point to the same place, node B. I guess it might look like they point to different places because to make things clearer, we've put A's next pointer at the top of B and C's prev pointer at the bottom. But that's just for the picture. Any data structure in any language, whether it's an array, a string, or a node in a linked list, has one and only one address. It's typically the address of the first byte of the set of bytes that the structure occupies, but whatever address it is, it's the only one that B has, and both of these pointers actually point to that same address in memory. If we show it accurately in the figure, it looks like this. What a mess. We're back to spaghetti again. Hey look, I got nothing against spaghetti. I love spaghetti. I'd like to have some spaghetti right now. But neatness is not spaghetti's long suit, okay? The point of this messy picture is just that you can't implement a doubly linked list without having more than one pointer pointing at the same address in memory. MATLAB won't allow more than one cell to point at the same address in memory, so if you decide to implement a doubly linked list with cells, it's game over before the game begins. To make this problem with cell pointers clear, we demonstrated it in our introductory course in Lesson 7 with the case of the missing strawberries. But we're going to demonstrate it again right now, this time with a card trick. First, let's pick a card. Okay, as you know, the braces around Jack of Spades means that instead of storing Jack of Spades inside the variable cell A, we've stored a pointer to it. Now let's copy cell A into cell B. Now let's make sure that these pointers are pointing at the same thing. Yep, the braces around the ones tell MATLAB that we want to see the actual card that the cells are pointing at. And we even used is equal to make sure that the addresses in these cells are equal. You know, I like spades, but I'm not all that excited about the jack. Let's change it. Again, the braces around the 1 tell MATLAB that we want to work with the thing that cell B is pointing at, and we change just the first 4 characters from JACK to KING. So now we got a better card. Okay, Ready for some magic? Let's use cell A to look at our card. What happened to the king? Quite a trick, huh? You could spend a lot of money on Penn and Teller in Las Vegas and not see magic better than this. I've been there. I've seen their act. It was a pretty good show, I have to admit. And I especially like it when Penn Jillette explains how a trick is done. Of course, they don't explain the best ones. But you're watching the Fitzpatrick and Leeditzy show, which is also a magic act where one guy does all the talking. But we explain all of our tricks. The secret to this trick is that even though it seemed like both cell A and cell B were pointing at the same thing, they were not. When we set cell B equal to cell A, instead of directly copying the pointer in cell A into cell B, MATLAB reached behind its back and quickly made a copy of the string Jack of Spades and then slipped a pointer to the copy inside cell B. So at that point, cell A was pointing at one Jack of Spades and cell B was pointing at another one. Oh, and the is equal thing? That was misdirection to distract you from thinking through what had just happened. I told a little fib there. Just for the sake of the trick. When is equal returns true for two cells, it only means that they're equivalent, which means that they point at data objects that are equal. It doesn't mean that the addresses in the cells are equal. And now that we know that cell A and cell B are pointing at different copies of the Jack of Spades, it's not surprising when we change one of them to the king to find that the other one remains the same. Well, that's our trick, and that's how we did it. And we showed you this little card trick to drive home the rule that no two cells can point at the same object. And my friend, you can try any trick you want to get around that rule, and that mean old Mr. MATLAB will slam the door in your face every time. But when MATLAB shuts a door, it usually opens a window. And in this case, the window is a special built-in class called the handle class. The handle class gives us exactly what we need to implement a doubly linked list. Of course, you've heard us use the word handle already in this course when we talked about function handles. And if you've taken our introductory course, you heard us talking about MATLAB's file handles. And MATLAB uses the term handle for other things too, like figure handles and axis handles, and such as that. All these uses of the word handle have the idea in common of one thing providing some sort of access to another thing. So, for example, a function handle gives you access to a function that allows you to call it, and a file handle gives you access to the contents of a file. A handle class is a new example of something that grants access to something else, with the important difference that you get access to an object. We'll look at an example of a handle class in a couple of minutes, but the first thing to know about them is that when you assign a handle object to a variable, the variable gets a pointer to the object instead of the object itself, just the way a cell variable gets a pointer. But with the handle object, you don't have to use those special braces to get the pointer. It just happens automatically. The pointer that it automatically gets is called a handle, and a handle includes the address of the object along with some other information. So the variable with the handle in it, which we'll call a handle variable, is similar to a cell variable, like cell A or cell B. But, and this is a big but, MATLAB allows two handle variables to point at the same handle object, which is why I said that it's exactly what we need to implement a doubly linked list. Let's see a comparison of a handle class and a non-handle class, which is called a value class. Here I've set up definitions of a value class named Mike on the left and a handle class named Akosh on the right. And you can see right here how we make a handle class. We use the less than sign and the word handle, which is the same syntax we use to turn our business contact into a subclass of the superclass named contact. This word handle is not a keyword. Well, I guess you can see that since it's not blue. Handle is the name of a built-in class, and to turn a new class into a handle class, you simply make it a subclass of the built-in class named handle. I've only put in these classes the minimum that we need to illustrate how a handle class works. They each have one property, and its name is card. And they don't have any methods because we don't need methods to show how a handle class works. Under each of these class definitions, I've placed a live script for trying them out, called try Mike and try Akash. Let's step through try Mike first. This first step assigns a Mike object to cool guy. And this next step copies the object in cool guy to another variable called cool copy. Now we'll change the property, just like we did with the cell variable. And we'll check the property using cool copy. Well, this is exactly what happened with the cell variables. When we assigned cool guy to cool copy, MATLAB reached behind its back and made a copy of the object in cool guy and slipped it into cool copy. So when we changed cool guy's property to king of spades, cool copy was still stuck with the jack. Now let's repeat these same operations with the handle class. The first step assigns an Akash object to other guy. And the next step copies the object in other guy into other copy. Again, we change the property. And again, we check the property of the other object. But this time, both objects get the king because other guy and other copy are handle variables, and they both automatically got pointers to the same object. Finally, we're getting somewhere. This distinction between normal MATLAB variables and handle variables has other important consequences too. For example, do you remember when we talked about the call stack in our first lecture on recursion? Yeah, that's what I thought. Let's review that, but this time we'll do it with objects. Here on the left is a function named setValue in the editor window with the command window below it. On the right side, the blue box represents the memory, with the call stack on the left and the base frame for the command window's workspace at the bottom. The rest of the memory is on the right. We first assign an object of value class to x and set a property named value equal to 2. We aren't showing the class definition because, frankly, we don't care what it looks like, except that it has a property named value. In the stack, we see x in the base frame holding as its value an object of type value class with its value property set to 2. Now we pass x as an argument in a call to the function setValue, and let's hit the pause button on execution right there. As we said in the recursion lecture, whenever a function is called, and this holds whether it's a recursive call or a non-recursive call, the function is allocated its own private frame on the stack to hold its local variables, including its arguments, and all the arguments are passed by value. The phrase by value means that the value in the actual argument x is copied from the caller into the formal argument y of the function setValue and pushed onto the stack. So what does the operation look like when the thing being copied is an instance of a value class? Well, it looks like this. As we learned with our jack and king card trick, MATLAB makes a copy of the object and places it inside y. Next, after the actual argument is copied into the formal argument, the body of the function is executed, and the formal argument's value property is changed to 3. But when the function returns, that formal argument is treated like any other local variable. It's popped off the stack, and it's thrown away. The actual argument x was never even touched by setValue. Its value property has exactly the same value it had before the function was called, 2. And that's the end of our review of the call stack. Well, at this point, you might be expecting me to say that handle variables are treated somehow differently from other variables when they're passed as arguments to functions. Nope, it's exactly the same deal. So what's the consequences of using handle variables that I mentioned? Well, we're about to see one. Here we have the same function set value in the editor window again, but in the command window, instead of assigning a value object to x, we assign it a handle object. Then once again we set its property value equal to 2. The difference is that, as we learned with the card trick, the handle variable x gets only a handle with a pointer to the object. The object itself is allocated some space somewhere in the rest of the memory, as we show here. Now we pass the handle as an argument and a call to set value. And once again, let's hit the pause button on execution. In the function call, the handle is passed by value, just like the object was in the example we just finished. So the function being called gets only a copy of the handle in its formal argument y. However, and this is a big however, that copy of the handle in the formal argument refers to exactly the same object that the actual argument does. And because they're both pointing at the same object, it's possible for the function to use the handle in its formal argument y to reach out and touch an object outside itself. In particular, it can change the values of its properties, and that's exactly what it does. When the function returns, the formal argument is, as in the previous example, popped off the stack and thrown away. As with the example with the value object, the actual argument, like all actual arguments in all function calls, was never touched by the function. It was the object that it was pointing at that was changed. So, and this is a big so, after the function returns, the property value of the object pointed at by the handle variable x has a different value from what it had before the function was called. And that ability of the function to change an object referenced by a handle variable is the consequence we were talking about. There are other ways in which a function can change variables outside its local scope. One is by means of global variables, which we demonstrated in our introductory course, but recommended that you never use. We looked at a much better approach in our lecture on nested functions in this course, which are functions defined inside other functions and which can access the variables in those other functions. The difference here is that the accessibility of the objects is determined not by where the function is defined, but by what type of input the caller passes to it. If it passes in a value object, the function cannot change it. If it's a handle object, it can. Okay, let's see this played out in an actual MATLAB session. Consider this class definition. We didn't put a less than sign here, so this is not a subclass of any other class, and in particular, it's not a handle class, so it's a value class. It has one property, which happens to be called value, and two methods, the first of which is a constructor. The constructor can be called with one argument or no arguments, and it initializes the value property accordingly. But the more interesting thing is the one called set_value, which is the same name as the one we use for the ordinary function in our schematic depiction. Note that this is not the official setAccess method that we introduced in our previous lecture. That would have the name set.value instead of set_value. No, this is just a method that happens to set the value property. Or does it? Let's try. Well, clearly it doesn't. And we shouldn't be surprised, because this is exactly the same thing that we showed you in our schematic depiction of what goes on when we passed a value object to set value. It looks a little different because this time the function that we're calling is a method, and we called it with the dot operator. But here, let me show you a different way to call the method setValue. Unless you work really hard and use some advanced tricks with your class definitions, these two calls will always be exactly equivalent. When you call a method with the dot operator, the object must come before the dot and the method comes after it. When you call a method using the normal syntax for a function call, the object must be an argument. In this case, it must be the first argument because that's how the function is defined in the class definition. And of course, since it's equivalent, it accomplishes exactly the same thing as the dot operator version of the call, which is, well, nothing. Let's put a breakpoint right where we try to set the value and see what's happening step by step. Okay, so we hit the breakpoint. Let's take one step. Then check the value property. So it's clear that setValue does set the value property to 3. But as we were reminded in our review of the call stack, the only object whose property was changed is the one in the formal argument here inside the setValue function itself, obj, not the one in the actual argument over here in the command window. Let's continue our execution and look at the actual argument after this function returns. Still equals 2. So that's MATLAB being its usual consistent self. Not that I believe that MATLAB's alive, It's just a metaphor. Although sometimes when I've been programming long into the night, I think I feel this presence. But never mind. The point is that you can't change an actual argument by changing a formal argument. By the way, if you have experience with object-oriented programming in another language, this may not be what you would expect. In that case, you'll just have to remember that this is how value classes behave in MATLAB. So is it even possible to change the value of a property of an instance of a value class from within its own methods? Well, yes and no. Let's change that to no and yes. No, the function can't do it, but yes, you can do it. You can do it in the same way that you make a change using an ordinary function with ordinary variables. Let's say, for example, that you've set the variable x equal to some number and you want to use the square root function to change x to the square root of x. You might do it like this. So we passed x as an input argument to the square root function, and then assigned the output from the function back to x. And that's exactly what we need to do with our setValue method in order to change the object. The method already takes the object as an input argument, so the only change we need to make is to have it also return the object as an output argument. Let's do that. Now we can use setValue to change the object in exactly the same way that we use the square root function to change x. And just to make sure that you believe that calling a method this ordinary way is the same as the dot operator way, same result. Of course, if we don't assign the value returned by the method to the variable, no change takes place. While the object that was returned in this first command does have a property value of 4, Brandon is still stuck with 3. Since this behavior is somewhat counterintuitive, we strongly suggest that when you're dealing with value classes, you use the ordinary function calling syntax like this, instead of the object.method name approach. Doing that will help you remember that you need to assign the returned value to the object if you want properties that are changed inside the method to be changed outside the method. So the bottom line of this example is that if you want to use a value class method to change a property, it must return the object as an output argument. That's the only way to make the change stick. By the way, this is a good time to answer a question that may be lurking in your mind, and that is, when you call the function the ordinary way, like this, without the dot operator, how does MATLAB know to look inside the definition of test class to find the method's set value? Well, for starters, MATLAB decides that set value must be a function when it can't find a variable by that name in the current workspace. That's nothing new. But after that, the data-centered aspect of object-oriented programming kicks in, because MATLAB then looks at the data to decide where to search for the function. In particular, it looks at the actual arguments to see if one of them is an object. And if one of them is an object, it checks to see what the class of the object is, and then searches inside the definition of that class for a method with the same name as the function. If two or more arguments are objects, it searches the class definition of the leftmost object. If it finds the method there, it runs it. If it doesn't, then it searches the path for the function, and if it finds one with the same name, it runs that one. Now, what if test class was a handle class instead of a value class? Let's try that. All we have to do is make it a subclass of the built-in handle class. And presto, test class is now a handle class. Let's remove the output argument from the setValue method. And let's create an object of this new handle class and call the setValue method. It worked. The same method that failed to do anything when test class was a value class changed the value parameter to 3 after we made test class a handle class. Of course, this should also not be surprising because, as we saw in our schematic example for the handle variable, the actual argument Brandon in the command window and the formal argument obj in setValue both contain handles for the same object. We used obj to change the object, and when we looked at it with Brandon, it still had the new value. This ability to change objects outside a function from inside the function makes handles very important and very powerful. But we have to be careful how we use that power, just like our favorite superheroes. My favorite superhero, when I was a kid, was Superman, hands down. The rest of them just didn't measure up. They still don't, except for one. And I think we can all agree that he is definitely the best. And of course I'm talking about Deadpool. Now that, dear friends, is a superhero's superhero. But getting back to the business of us mere mortals, the reason we have to be careful with our newfound handle power is that now we can write functions that change values in the caller's workspace with nothing in the caller's code to indicate that anything has been changed. That stealthy behavior can cause confusion and bugs unless we're super careful with our superpower. In order to make the difference between value and handle classes more apparent in your program, we would advise you to use the dot operator to call a method only for handle classes, and stick with the old all arguments in parentheses way for value classes. And remember that if you want to use a method to change a property of an object of a value class, then it needs to return the object. And now that we know all this stuff about passing objects to and from methods, let's get back to linked lists. There are many ways to implement a doubly linked list in MATLAB or in any other object-oriented programming language. For example, the order of the next and previous pointers can be changed. Their names can be capitalized, and other properties can be added to the nodes. But when I look at this picture, two separate classes suggest themselves. One for a single node and one for an entire list. A node is conceptually different from a linked list of nodes. A node has some kind of data and a next and prev pointer. And from here on in, we're going to use the terms pointer and handle interchangeably because we're going to use handles to implement pointers. The list itself has multiple nodes, plus a head and a tail. So let's create two classes, a doubly linked list class, which we'll call dlist, and a node class, which we'll call letterNode. But before we create either of those classes, we're going to create a superclass called LinkedNode. As you can see, it's a handle class, and it has three properties: prev, next, and owner. The first two have obvious uses. They provide access to the previous node in the list and the next node in the list. But what about this owner property here? Well, it's going to provide access to the linked list that contains the node. Since each node has only one next handle and one prev handle, you can prove that a node can be in only one single linked list. And having a handle to access the list is going to be useful, as we'll see shortly. We've also included a constructor that simply initializes each property to the empty array. That's not strictly necessary because that's what MATLAB would do anyway, if there were no constructor provided. But it doesn't hurt either. We don't need input arguments for sure, because at creation time we don't know how those properties should be set. They'll only be decided when we insert the object into an actual list. So what about the data? We're working hard to create a linked list that stores data. So where is it? Well, it's too early to tell. Or to put it in another way, we want this class to be flexible and to be able to store all kinds of different data. What that means is that we never want to create an object of type linked node directly. We want to be able to design subclasses of it. Those subclasses will specify what data they can store. But they will inherit the behavior from our linked node class here that lets them organize their instances into linked lists. Well, not yet though. We have quite a bit of work to do before that happens. Let's work on the actual list class next. Here's our first version. It's another handle class, and the first part is pretty easy. It's got three properties: head, tail, and length, and its constructor sets head and tail to the empty array and sets the length equal to 0. But now comes the interesting part, the method that inserts a new item into the list. In this first version, the insert method always puts the new element at the end of the list. The first statement of the body of the function insert might need a little explanation. As we said earlier, a node can't be linked into two lists at once, and to enforce that rule, we start by checking to see whether it has an owner. If it does, then we check to see whether its owner is the list we're adding it to, and if so, we don't need to do anything to insert it, so we return. If it's owned by some other list, we remove it from that list. That's done by this statement: node.owner.remove node. This is the first time we've seen the dot operator show up twice in one statement in object-oriented programming. As we learned in our introductory course, MATLAB always uses left-to-right associativity, which means simply that the left dot operator operates before the right one does. So node.owner is evaluated first, and the result is some other dlist. Now the second dot operation is carried out with this resulting dlist on the left and the method named remove on the right. As we've explained before, when MATLAB sees a function like this remove, it checks its input arguments to see if any of them are objects, and the operand to the left of the dot operator is one of the input arguments of the method. And since it's an object, MATLAB executes its remove method. Okay, what I'm about to say may be hard to hear, but the fact is we don't have time to continue with a detailed line-by-line explanation of every operation on every line of every function. No more spoon feeding, no more baby steps, no more training wheels, no more metaphors. Wait, one more. No more water wings. This is, after all, an advanced course. So except for the introduction of new concepts, Akash and I are going to leave you to figure out the details on your own. The comments should help, of course, and you can either pause the video or look at the files online on the course website when you need to study the code. As you study this function, note that when we update the various head, tail, next, and prev pointers, we have to be careful of the order in which we do it. For example, in this function's other double dot statement, we use the tail handle of our list to get the next handle of the node that's currently last on the list, and we use that handle to point that next handle at the node we're inserting, after which we update the tail handle, all in that order to avoid having the node point at itself. Oh my gosh, even I didn't understand what I just said. Good luck, Lieutenant. To continue in the on-your-own vein, we'll let you figure out the remove method that the insert method calls. The next logical step would be to test these methods. We can't do that just yet. First, we need to create a subclass of linked node that stores some data. Remember, linked node is not supposed to be used directly to create instances. We're going to define subclasses of linked node with places for data and create instances of those. For simplicity, let's use a trivial class that stores just letters. This class looks too simple to be worth anything, but don't forget that it inherits all the properties and all the methods of its superclass, linked node, and they're added to the one property, letter, and one constructor method that we encoded explicitly in its definition. By the way, we could have added some code in the constructor to throw an error if the input argument in the constructor is not a letter, but we'll let that slip for this simple class. Okay, now we're ready to create a linked list, that is a D list, with multiple letter nodes. I prepared a live script that we can step through. We'll clear the memory, set my list equal to D list, and of course there's nothing on it. Let's get something to put on it. We'll put a letter node containing the character A in the variable A, and a B in B, and a C in C. Now let's insert the nodes into the list one by one. We insert A, we insert B, we insert C. So it says it has 3 elements. So far, so good. There should be an ABC order since insert adds its element at the end of the list. Let's see if they are. Look at the head. Yeah, that's A. Now let's look at the next node after the head. That's B. And the next after the head, and that's C. So that's good. Well, what about the end? MyList.head.next.next.next. That should be the end, and sure enough, we've got the empty array. So farther, so better. Now let's go backwards. Ooh, how about that? 4 dot operators in one expression. 5, 6. Just remember to think about what those dots are doing, going from left to right, one step at a time, and it's simple. The first one jumps back to B, and this one goes back to A. Do it one more time, and we're back to that empty array at the beginning. All right, seems perfect so far. Now, of course, we'll have to admit we didn't write this code perfectly on the first try. There were quite a few bugs, but it looks like we've killed them all. Famous last words. Let's test the remove function. We'll remove A, and let's look at the head of our list. Well, there's B, so A is gone. And let's go back one from there using prev, and we're at the beginning. Now let's go to the next element after the head. That should be C, and it is. Removing the head worked. How about removing C from the tail of this two-element list? Let's see, there should be just one node left. Let's see if that's right. Yep. And just as a sanity check, let's make sure that removing A and C has left B at the head of the list. Check. And that there's no next element or previous element on this one-element list. Check. And can we remove B? Sure can. And we have a list of length 0. And now do we still have our letter objects? Let's see. Oh yeah, they're all still sitting there, and their next prev and owner handles are all set correctly to the empty array. So, we've created our very first linked list, and then we removed every node from our very first linked list. The programmer giveth, and the programmer taketh away. Okay, these three handle classes let us do everything we need to do to work with a doubly linked list. So our setup here is in pretty good shape. Well, yeah, pretty good, but it could be better. On the plus side, we can do everything we need to do without ever having to assign a value to any of the properties directly. So, for instance, we never had to give the command mylist.next equals the empty array. That's good, because we'd have a tough time keeping track of which handles need to be set to what anyway. It's better if the program does that automatically. And if we don't need to set these properties, we're much less likely to make mistakes setting these properties. Like, say, I don't know, setting the head of the list to the number 42, or some other random value. On the minus side, I could make mistakes by, say, setting the head of the list to, I don't know, the answer to the ultimate question of life, the universe, and everything, instead of the correct handle. Fortunately, we can make it impossible for me to make mistakes like that by making it impossible to use mylist.head or mylist.tail or mylist.anything outside of the functions in the methods section of dlist. So the insert and remove methods will be able to use these dot operations according to the well-defined rules of our linked list data type, but statements outside the class definition will be denied access. We learned in the last lecture that we can add access methods to the methods section to intercept attempts by the user to access properties directly with a dot operator. And we could write access methods that throw errors when a user tries to do it. But there's a much easier way. All we need to do is open up the dlist class definition and set a so-called attribute after the properties keyword. And we do it like this. Access equals private. The parentheses are required, the A must be capitalized, And what looks like an assignment statement is actually a declaration that the access attribute for the properties of this class is being set to private. And with that, we have just put up a privacy fence that keeps prying eyes and grasping hands away from our private property. So what happens if someone tries to peek at one of the D-list properties? Well, let's try the head pointer. No public property head for class D-list, and that's red, so it's an error. And this error message actually reveals a lot. First, it obviously tells you that the head is not a public property. Second, it tells you that a property can be public or private, but not both at the same time. Third, it tells you that properties with no declaration are public by default. Fourth, it tells you that it must be possible to have some public properties and some private properties in the same class definition. And fifth, it tells you that when you make a privacy declaration, it affects objects that were already defined. It's pretty amazing how I can rattle off all these deductions right off the top of my head, isn't it? It's like I'm reading a script or something. Anyway, this privacy fence is really opaque, as you'll see when you try to look at my list itself. This statement tells you that my list is an instance of a class that has no properties at all. Well, that's just a lie. But it's a white lie. It's not meant to do harm to the user, but to keep the user from accidentally doing harm to D-list. But can we still add items to our list? Well, yes, we can. Of course, when we ask what my list looks like, it says there are no properties, but it doesn't say that nothing has happened. Of course, it's not obvious that anything has happened. But we've also provided in this class a method that displays relevant information. It's kind of like the print name method in the previous lecture. And here it is. It's called display list, and it uses a while loop to go through all the elements of the list, calling MATLAB's built-in display function named DISP, to display each one. By the way, notice this statement here, item equals item dot next. This statement replaces the current item with the next item on the list, progressing through the list until we finally get to the empty array, which makes the while condition false and stops the loop. This while loop with this while condition at the top and this item equals item dot next command at the bottom is a standard technique for traversing a linked list from beginning to end. Let's test it. And it works with no surprises. By getting back to the private declaration, we've put a fence around D-list, but we haven't done that for letter node. And as a result, when DISP displays a node, it can see its properties and prints them out. But that's not actually good, because it means that the user can see them too, and could potentially set them to bogus values, like 42. We can protect the letter property from mischief by adding a setAccess method and a getAccess method. We showed you how to do that in our previous lecture. But we'll leave that for another time. So for now, all we have to worry about are the prev, next, and owner properties that letter node inherits from link node. Let's build a fence around those. Did it work? We're not seeing the prev, next, and owner properties anymore, so yes, it worked. But, okay, look, of course it did. I know what I'm doing here, okay? And to prove it, let's run display list again. And this time you'll see only the letter property appearing for all three of its nodes in the list. Okay, well, I guess I kind of forgot one little thing here. Not only have we stopped the user from accessing prev, next, and owner, we've stopped, well, everybody, and that includes dlist. So now the while loop here in dlist can't use the dot operator to access the next handle because the next pointer and all the rest of them are hidden. We need to hide the properties in linked node from the user, but not from dlist. How can we do that? Well, things might get a little weird here. We replace the word private in this property declaration with $dlist. This $dlist syntax returns a so-called metaclass object. It's a metaclass because its objects are classes. So $dlist returns the class dlist. And the statement access equals $dlist means that only dlist has access to the properties. So we built a magic privacy fence that only dlist can see through. Did I mention that things might get a little weird? If we need to provide access to multiple classes, we can use a cell vector of the needed metaclass objects. Okay, but did this actually work? Have we fixed our problem? Yes, it did, and yes, we have. One final tweak for this lecture. The length property of dlist is private. On the one hand, that's good because nobody should be able to modify that number directly. On the other hand, users of our class would probably be interested to know how many elements that the list contains. So let's provide a method that returns the number of elements currently on the list. Our initial thought might be to provide an access method like we've done before using the get.length syntax. That's not going to work though because length is private and MATLAB will not allow accessing it even if we provide an access function. Instead, we can simply write a regular method that returns the value directly, like this. Since this functionality is similar to the length function we've used so many times on vectors, the same name makes sense. Let's test it. Well, it works, and we can use the alternate syntax with this function, which is so familiar to us from our many uses of the length function with vectors. Now that qualifies as cool. Well, there's still room for improvement for our doubly linked list data structures, but we've covered more than enough for one lecture. We've learned about doubly linked lists and that MATLAB's cell data type can't be used to implement them. But then we learned about handles, and handles are a big new deal. Like cells, they can hold pointers to other things, but unlike cells, two handles can point at the same object. And that one seemingly small feature gives handles great power, including the power to implement a doubly linked list. And we also learned that when a handle is passed as an argument to a function, that function can reach out and make changes to objects that are accessible by the caller, a potentially disruptive superpower that we must use very carefully. Finally, we learned how to declare properties in a class definition to be private, meaning that they can be accessed only by methods inside the class that they're defined in. And we learned about semi-private properties that can also be seen by methods in additional specifically named classes. So that's it for object-oriented programming. Just kidding. You really don't want to miss the next lecture in this exciting series when our hero rides again in the thrilling adventure entitled More on Object-Oriented Programming.